He's a new kid on the block. Also, in our session on difference equations and applications from combinatorics, or I forget, number theory. I see. So, so he's going to continue on his work together with Candace Kent on boundedness on max type equations in reciprocal form.
Thanks, Mike. So this is, like he mentioned, this is joint work with Candy, and this is really kind of building on some of the ideas that she talked about in the previous talk. This is self-contained, but the idea was they had looked at sort of the case where the recursion depth was 2, or more generally where you're just taking the max over 2 terms. And this is going to be looking at a more general context. So a very brief history, sort of the simplest type of reciprocal type difference equation is this. You just take the reciprocal of the previous one, you have some initial condition, but that's actually a very boring, right? So then you can say, okay, well, let's try something a little bit more interesting. You know, let's make it a deeper depth, but still that actually turns out to be really boring because it's just 3 of the previous one just kind of interleaved, right? So in order to get some sort of complexity, you need to do something different, something more complex. And so that gets you into the idea of taking the max over reciprocals of lots of previous terms. Because if you're not taking the max, then you can sort of run it forward and backwards, and there's just not very much going on there. So we jump way ahead over most of the history that Kenny talked about last time, and we get to this much more general form. Okay, so here what we're saying is you take the max over the reciprocals of the t previous terms, and each of them you're multiplying by some constant that's coming from some coefficient sequence. And you can use different coefficient sequences for how many terms previous was this term. Okay? And what we're going to focus on today is the case where, first of all, everything is positive, kind of what she talked about. And specifically, we're going to focus on the case where the AI ends are periodic. So they can have, each of them can have whatever period, and I'll get into that a little bit more. They don't have to have the same period, they can be different, but we need them all to be periodic to be able to say a lot in the framework we're going to look at. So, so this is a pretty general form, not quite as general as what she has up here, but and the reason that we're going to jump to that is this amazing result of Bidwell and Frankie that she mentioned. If any solution to this equation is bounded, then it is eventually periodic. Okay? So that tells you a whole lot about this class, but it does not tell you when the solutions to this are going to be bounded. And so what we're going to do is we're going to look at and say, in terms of this, this parameter sequence, these parameter sequences AIN, if we put some conditions on that, we can prove that these solutions are always going to be bounded. And then by their result, because they're bounded, we'll know that they're eventually periodic. So that's where we're going. So that's the main theorem of the talk today. Boundedness, if the periodic coefficients AN are nice, which I'll describe more formally later on, but for the time being, it's just something nice. If they satisfy some condition, then every solution has to be bounded. And so then by the Bidwell and Frankie result, they have to be periodic. Okay. So a very brief sort of general outline of what we're going to do. The proof outline is this. We assume that you have some solution that's unbounded. And as she mentioned, persistence and boundedness are the same thing, essentially. So boundedness, you know, persistence means that you're bounded above 0. And the idea is if you have some sequence that's going off to infinity, the only way you got there was by some subsequence that you were taking reciprocals of that were going to 0, and vice versa. So they end up being if and only if. You're bounded if and only if you're persistent. So we assume that you're unbounded, and then we pick some epsilon, which we'll decide later, and we find the first term in the sequence where you go smaller than that. And then we're going to prove some magical lemmas, which we'll get to in a minute, that say, in fact, once you have this first term, you can roll back C terms earlier in the sequence, and that term will be at least as small as the term here. And so it's going to contradict the idea that this was your first term that was less than epsilon. Right? Because this term here was already no bigger than that term later on. And so we're going to get a proof by contradiction. That's the very general outline. the details that I have to fill in are these magical lemmas that will imply that you can roll back. Yeah?
I view this almost like a proof by descent.
I have to think about that.
Okay.
I don't see that right away,
Okay.
but it's possible.
Okay.
Sure. Okay, so basically what I want to do for you is there's going to be sort of two lemmas that will give us this kind of conclusion. And then once we have this conclusion, then on the final slide I'll kind of show you how we put it all together to get the result. So we want to determine these xi's. Well, you have a formula for determining the xi's. But what I want to do is I want to roll it backwards. So I want to somehow say, we know this term in the sequence, in the solution sequence. Let's go backwards and see what we can say about the previous terms. Okay? So here's a statement of the lemma. You can read that if you want, but let me jump to a picture. And we'll kind of try and talk about what this is saying in terms of the picture. So the way to think about this picture is that this is log paper. And this here is 0. So the log of it is 0, so this guy is 1. The stuff up here is really big numbers, and the stuff down here is really small numbers. Okay? So what are we doing? We take some term that's less than epsilon. Epsilon's going to be really small. So our first guy here, this is x pt plus 1, is way down here, because it's really small, because it's less than epsilon. Okay? And now what we're going to do is we're going to work backwards, and we're going to say, okay, these three terms in general, these t terms, are going to be really big. Okay? And then this term before that, so this is the picture is the case t equal 3. So this is jumping back t plus 1 terms earlier. It's really small. And then before that you get t terms that are really big. Before that you get a term that's really small, and then really big, and really small, and really big, and really small, and so on. So, okay, so let's unpack this a little bit. What's going on? So this guy here, this is where as k runs through some range, so there's p terms in this range, right? So in our case, p is going to be like 5 or something like that. And basically what this is saying is all of these terms where the index is a multiple of t plus 1, which are these guys down here, they have to be bounded above by epsilon times some constant. So basically what's happening is this one's epsilon, and then as you roll back t plus 1 terms earlier, this one is bounded above by epsilon times r. It's going to put in p minus 1 here, the p and p minus 1, and you get r to the 1. And then as you go back another t plus 1 terms, you get an r to the 2. So basically they're all bounded down here, but you're sort of losing a factor of r every time you go back t plus 1 steps earlier in the sequence. Okay? And then what this is saying here is, really what it's saying is that all of these guys, when you took the min, so these each of these is defined, right, in the solution to what we saw on the previous slide. It's a solution to this, right? So what you're doing is you're taking the min over a whole bunch of terms. You take the reciprocal, okay, and so what's the thing we're taking the min over? We're taking a min over the reciprocal of all of these. So if you want this one, you take the min over this one, and that one, when you take the reciprocal, right? And so these guys are really big, which means if you take the reciprocal, you get something really small. This one is really small, which means you take the reciprocal, you get something really big. So when you take the max over all those, it's going to always be the small one that you're defined in terms of. And that's what's going on here. That's how we know the exact value for these guys. Does that kind of make sense?
Mm-hmm. Yeah.
General picture? So that's really what this is saying, but I find it more useful to think of it just in terms of this picture. And so now that we kind of have the picture in mind, let me go through a few more of the details. I'm not going to actually prove this, but I'm going to kind of work an example for you to kind of show you how. So the way that you would prove this, it's an inductive proof, right? And you sort of start at the end and you induct backwards. So let me actually just kind of work an example. So let's say that epsilon here is 10 to the negative 1,000, t is 3. So one interesting point about this idea is that what the actual coefficient sequences are don't really matter very much, right? You can essentially compared, if you have it in the range 10 to the 3 to 10 to the negative 2, this is essentially almost constant compared to this here, right? So the asymptotics, this is so small compared to that. And we're going to choose that epsilon, so that it's really big in terms of where this coefficient sequence is bounded within some bands. Okay? And we don't actually care what the coefficient sequence is. All we need is some upper bound on them and some lower bound on them, because we're just going to be proving inequalities. Okay? So let's say x60 is less than 10 to the negative 1,000. Well, x60 is defined as the max of these reciprocals, and the A star star just means don't pay attention to what the actual indices are. We're just going to use these two bounds. Okay? So what is this saying? So this is saying that x59, x58, and x57 have to all be, so each of these three terms has to be less than 10 to the negative 1,000. Right? Well, because these coefficients are all bounded below by 10 to the negative 2, you have to get a factor of 10 to the negative 998 by dividing by these guys down here. So all of these three things have to be really big. They all have to be at least 10 to the 998. Right? And so this is, x to the 60 is our first small dot, and then these three are our big dot, our high dots up here. Right? And then we're going to roll back a little further. Now let's look at x59. So we know x59, 58, 57. Now we look at x59. Well, it's defined in terms of the max of the reciprocals of 58, 57, and 56. We know 58 and 57 are really big. So if you take reciprocals of those things, you get something really small. Right? But we know that 59 is really big. So it can't come from this one, it can't come from this one, it must come from the x56 term. So the x56 term must be really small. How do you get that small? Well, x59 is at least 10 to the 998, and you can get at most a factor of 10 to the negative 2. Let's see. Let me make sure I'm saying that right. You can get at most a factor of 10 to the third. You're trying to get really big. You can get at most a factor of 10 to the third from the A's, which means that x56 must be at least this big or smaller. Right? So that when you divide by it, you get this factor of 10 to the 995. Does that make sense? Mm-hmm. Yeah. All right? And so you can kind of just iterate this. And you roll back further and you basically make the same argument. So basically this is the same thing as this 10 to the negative 1,000. You're just off by a factor of 10 to the 5th. Right? And this is the same as that. You're off by a factor of 10 to the 5th. Where is 10 to the 5th coming from? Well, it's 10 to the 3rd divided by 10 to the negative 2nd. Yeah. Right? And that 10 to the 5th, that's that factor of r on the previous slide. Every time you roll back t plus 1 terms, you lose a factor of r in the bounds. Okay, so, and then further, now let's look at x59. We said that we could actually tell you exactly what it was. It was in terms of x56. Well, why is that? Well, if you look at x59, you know that these two terms they're dividing by something really big, so they're going to be really small. This one is dividing by something really small, so it's going to be really big. So obviously, the max of those three is going to be this one. Okay? And it's a similar thing. It works out the same way for x58. Well, what is x58? Well, x58 is in terms of x57, x56, and x55. But you know x57 is really big, you know x55 is really big, and x56 is small. So in this sort of process, you can figure out exactly that all the terms that aren't, where the index isn't a multiple of t plus 1, it comes from a previous multiple of t plus 1. Okay. So, etc., etc. And this is induction, it's the way you make this formula. So that's the first lemma. So let me talk a little bit about the second lemma. So, and again, I'll tell you what nice means in just a minute, but it's some condition on the periodicity of these coefficient sequences. So let the A's be nice. We're going to define some constant as a function of those periods of the sequences. And now the thing to look at this, don't pay too much attention to what this says. The important thing to note from this is that this hypothesis is the conclusion of the previous lemma. So they dovetail together. So if you satisfy the hypothesis of the first lemma, you get this out as the conclusion of the first lemma. And then you put this in as the hypothesis of the second lemma, and you're going to get this out as the conclusion. Okay? So, again, so let's jump to the picture. what are we going on? So this is the picture we had coming from the first lemma, right? And what is this saying? This is saying that xpt plus 1, this dot way back here, is greater than or equal to x0, which is this dot here. Okay? So we rolled back that many times. So basically, we had this picture before, and now what this lemma is saying, well, let's change it, we can actually get this picture. So that's the change. Yeah. That one dot, right? Just 1 second. So the point is, this information that we have in this picture, it's not exact. What we know is these are bounds away from the center line, right? So these are bounds below and these are bounds above. So basically what we did is we just improved the bound. So this picture was fine, this picture just has more information. Okay? And the key is now, this is going to be our first time we go below epsilon, and we're going to say, oh no, this time we went below epsilon sooner. That was earlier in the sequence, and that's how we're going to get the contradiction. Yeah?
I was just 5-minute warning.
Okay, cool. All right, so let me, so now, how are we going to prove this? The basic idea is that we're going to unravel, we're going to unroll the recurrence, right? And so x60 is defined in terms of max of these things, and for each of these things, we know that this is actually defined as something over x56, right? Because that's t plus 1 terms earlier.
Yeah.
And so when you do that, you get a x56 in the denominator of the denominator, which pulls out to be in the numerator, and then you have the max over just some ratios of coefficients. And then you can unroll that again, and you can keep unrolling it and get all the way down to x0 times some max of some stuff. And what we need to show is we need to show that the max of this stuff is greater than or equal to 1. Right? Because what will that give you? That will give you this x60 in our case is greater than or equal to x0 times something that's greater than or equal to 1. We'll give you that. Okay? So let me briefly show you sort of how we some example of how we get this, that this is greater than or equal to 1. Okay, and I'll sort of tell you a little bit about what it means to be nice. So for each of these AIs, we're going to let PI denote the period of that sequence of coefficients. So the AIs are nice if there is some J, some index on the different, some sequence, such that if you take the GCD of t plus 1, which is the depth of the recurrence, and the product of pj and t plus 1 minus j. So let me just give you an example. Then those are relatively prime to t plus 1. So here's my example. I have a recursion depth 3, and I've got A1 is 2, 3, 12 repeating. A2 is 1, 20, 4, 10 repeating. And A3 is what you see there. So now, what do I get? P1 is 3, P2 is 4, and P3 is 5. So if you take the product of 3 and 5, that's 15. That's relatively prime to 4. 4 is the t plus 1. And so because 15 is relatively prime to 4, then these A's are nice. And that means that what we said on the previous slide is going to hold. Okay? So basically, what happens, so I said you could keep unrolling this thing, and if you unroll this recurrence, this is the thing that you get out. That's kind of a mess. Okay? But fortunately, what you can do is, you're taking the max over a whole bunch of things. So if we just want to lower bound it, we can pick any particular term we want in here and any particular term we want in there, because we just want a max. We just want a lower bound. So we pick some particular term and say, okay, let's just do that one and that one. And then now what we'll get into when we jump from here to here, so basically we can clean some of this stuff up. And the reason that you can do that is because these periods of these coefficient sequences are relatively prime to t plus 1. So this boils down to some fairly simple idea in algebra, just that essentially that the period of the sequence is an additive generator of the group, essentially. And so you're going to get all of the terms in the group showing up the same number of times. You can make a similar argument and get just the reciprocal of this coming out. And the point is that if you take the max of two things that are reciprocals of each other, at least one of those is going to be greater than or equal to 1. Okay? All right, so let me kind of put this all together and wrap it up for us. So this is lemma 1 and this is lemma 2. Again, the conclusion here is the hypothesis here. And so what that means is that they dovetail together very nicely. You say, if the AIs are nice, then there's some integer, some positive integer, and some epsilon, such that if you go out at least so far in the sequence, then when xn is less than epsilon, then you can jump back this many terms. And this guy earlier is no bigger than the guy xn. That's the big conclusion, and that basically just comes from dovetailing those two lemmas together. Okay? So let's use that conclusion now to come to the big payoff. So this is what we wanted to prove. If the periodic coefficients are nice, then every positive solution of 1 is bounded. Okay? So what are we going to do? Well, just what we said on one of the first slides, we assume that this subsequence is unbounded, which means that there is some subsequence, that the solutions are unbounded, so there's some subsequence that goes to 0, that does not persist. This is, the only way you can get unbounded is if you're taking reciprocals of things that are going to 0. And so now what we're going to do is we're just going to choose some subsequence of these guys that doesn't persist. We're going to choose a greedily decreasing subsequence. Right? So basically you just look at the next term in this subsequence and you say, if this is smaller than everything else previously in, you put it in. Okay? So maybe this is your sequence, and then xnk, this is the greedily decreasing subsequence. We have 1, 4, 5, 8, 11, 63, 66, whatever goes in. Now, what we want to do is somehow we want to get a contradiction. So here, again, t is 3, and from our corollary, we get out some p. So let's say p is 15.
Okay, all right, and how do I start it?
And we look for the first guy in this subsequence as we're going out that's less than epsilon. Okay? So now what do we know? We know from our lemma that x66 is greater than or equal to x66 minus, this is the p, and this is 3 plus 1 is the t plus 1. So what we're saying is that x66 is greater than or equal to x6. Okay? And so now our question is, what's going on with x6? Well, we know, in this case, we know x6 is greater than or equal to x5. Because if x6 wasn't greater than or equal to x5, then we would have put it in this black subsequence. Right? The black subsequence is the greedily decreasing. It's a similar case. If it's already in, then that's fine. But, so x66 is greater than x6, and x6 is greater than or equal to x5, but x5 was greater than or equal to, was greater than x66.
Yeah.
Right? And so, that's going to give us a contradiction. And it's a very similar thing. If x6 is already in, then you have x6 is strictly greater than x66. But x66, by our lemma, is greater than or equal to x6. So again, you get the contradiction. So that's it. Let me stop there, and then if we have any questions. Thanks. Yeah.
How did you choose the epsilon?
How did I choose the, which one?
So
How did I choose the epsilon? So the epsilon here, I didn't say what it was, but it comes out of, where did we go? It comes out of the first lemma. That there exists this epsilon greater than 0, right? And intuitively, the way you're going to choose this epsilon, so I showed on this previous slide, what I said was that epsilon is going to be small compared to these guys. right? So what I do is I look at the max, I look at the min, and then I also basically need to make the epsilon small enough that when I keep losing this factor of r, as I go back p times, I still want to have lots of control, right? I don't want this thing, I don't want r to the p to get anywhere near as big in magnitude, or its log to be as big in magnitude as epsilon, right? I want epsilon to dwarf this r to the p. And so basically, I figure out what is my r going to be, what is my p going to be, and then I pick some epsilon so that it completely dominates those things.